start it. Paul, please also start yours. Okay, so today's Symmetry Seminar is by Ryohei Kobayashi from the IAS, and he'll talk about soft symmetries of topological orders. Please take it away.
Yeah, thanks for introduction. And thanks for having me here in the very nice conference. I'm very delighted to be here. So today I'll talk about some global symmetry of the topological ordered phases, TKFT, with some rather exotic properties. So this is based on my recent work in January, which is done with the Mason in Maryland. So, okay. So let me get it started with some a brief intro on the topological order and its symmetries. So the topological order is just basically a non-invertible gapped phases of matter, which is found in the quantum many-body systems. So this is non-invertible, so it carries some ground state degeneracy of the ground state of the gapped systems, and importantly, this degeneracy associated with a spontaneous breaking of the zero-form symmetry in the usual sense. So it's outside of the classical sense of the random paradigm, and it is some genuine topological phases of matter without the ordinary spontaneous breaking of the symmetry. And then there are usually zero quasi-particles, which is called anyons, and at the field theory level, this anyon can be regarded as some endpoint of the topological line operator, which is present in the TKFT. So today I'll be mostly interested in the global symmetry, invertible zero-form global symmetry of these topologically ordered states, mainly focusing on 2+1D and comments on the higher dimensions later. And so the 2+1D TKFT generally has lots of the zero-form symmetry, though there's no local operator to be acted on. So though there is no local operator that is charged under the global symmetry in the 2+1 dimensional TKFT, zero-form symmetry can still act on anyon in various ways. So, and there is a beautiful theory of the zero-form symmetry of the topological order, which is algebraically described by the symmetry fluctuation theory or G-crossed radial diffusion category or blah blah blah. And so let me just give you the several well-known example for the global symmetries. So I think the most simplest example of the global symmetry in the topological order is that we consider the Z2 gauge theory in 2+1D, where we have a gapped electric particle and a magnetic particle. And there is an emergent Z2 symmetry which permutes electric and magnetic particle, which is sometimes dubbed electromagnetic duality that exchanges E and M. This is a Z2 gauge theory, a Z2 symmetry of the Z2 gauge theory. And also, so this is an example where the symmetry permutes labels of anyons. But but even if there is no permutation of the label of the anyons induced by symmetries, the symmetry can still act on a non-trivial way. For instance, in the case of the fractional quantum Hall states, the theory is effectively described by some Chern-Simons theory, and there's some bunch of anyons which is carrying fractional charges under the U1 global symmetry. So in this case, even if the U1 symmetry doesn't permute anyons since it's continuous, but there's still a non-trivial fractional charges carried by the anyons. Right. So these are kind of well-known examples of the action of the global symmetry on the topological phases, like permutation of anyons or fractional charges. But in this talk, I will discuss a rather exotic example of the global symmetry in the topological ordered phases, where the symmetry doesn't permute anyons, or there's no fractionalization of the anyons, in the sense that the anyons doesn't carry any fractional charges under the action of global symmetry. So while this symmetry action looks almost completely trivial, this kind of symmetry can still act faithfully on the Hilbert space and generates a non-trivial symmetry action. And so this kind of symmetry is like inspired by the like prior discussion by Davidov. He's a mathematician, and he studied like a symmetry of the 2 plus 1 dimension TKFT, which doesn't act on a torus, which sort of trivial. Just looked into the some Hilbert space on torus, but there is more subtle symmetric action, which he called the soft-braided O2 equivalences. And some of the soft-braided O2 equivalences he studied satisfy this property where the no permutation of the anyons, no fractionalization of the anyons.
Sorry,
So
can I ask just a
sorry,
question
yeah.
on the terminology? So in your definition of global symmetry of the TKFT, are you only including invertible symmetries?
Yeah, I'm only
Okay.
including invertible symmetry
Thanks.
here. Yeah, so in this talk, I'm mostly talking about invertible
So you will not
symmetries.
include condensation defects of the TKFT.
Well, some of the condensation can be also regarded as some invertible symmetry can also be regarded as like a condensation defect with some. Yeah,
Sure, but the most general condensation will have some kernel. So
right, I'm not talking about the like no invertible symmetry here. I'm just talking about the like invertible stuff.
Thanks.
Right. So actually, so when David talked about this soft-braided O2 equivalences, he didn't like refer to the symmetry fractionalizations, but in this talk, I will discuss like a physical perspective of this kind of like soft-braided O2 equivalences, or like this kind of a soft action on the anyons, which is a kind of extremely subtle. So any other question on this intro? Okay, so let me go ahead.
Sorry,
So this
a
kind
quick
of
question.
yeah.
Maybe you will explain this afterward, but typically I think about the Hilbert space of a TKFT as being generated by insertion of line operators, like if the so I am a bit confused how it's possible that the symmetry acts on the Hilbert space but doesn't act on the anyon, because I used to think that the action that the symmetry has on the Hilbert space
Yeah, sure.
can be recovered by the action on the anyons.
Right. So I guess you are talking about the action on the levels of the anyons. So sometimes but even if the a permutation action on the anion is trivial, later I'll explain that a symmetry still acts non-trivially on the a junction of the anions, like a fusion vertices of the anions. And then in the case of the soft symmetries, this is a non-trivial data of the symmetry action. I'll explain later about this point in detail. Yeah, thanks for the question. Okay, let me go ahead. So this kind of soft symmetry can be actually found in the some specific finite case theory. So let me briefly review what is like an invertible global symmetry of the finite case theory. So let's consider the a finite gauge theory of the gauge group G in the generic dimensions. So here I'm not actually really talking about the 2 plus 1D, it can be generic dimensions. So its zero form invertible symmetry generally contains these guys. So one of the classes of the invertible symmetry corresponds to the other automorphism of the gauge group. So this out G, this is like an invertible zero form symmetry, which acts on the gauge fields by some other automorphisms. So the simple example is you take two layers of the Z2 gauge theory, which is Z2 times Z2 gauge theory, just a stacking of the Z2 toricals. And then we can obviously consider some symmetry which swaps two layers. These layers, this swap operation is automorphism of Z2 times Z2. So this is an example. And also if you consider the n gauge theory, or even non-finite U1 gauge theory, there's a charge conjugation symmetry. This charge conjugation is an example of the automorphisms. And the other guy, which is labeled by the group cohomology, like HD, and like a group cohomology of G valued in 1. So this is a label of, this is a classification of the SPT in these spacetime dimensions. So this basically corresponds to some decoration of the SPT. So physically, so this defect can be understood as follows. So let me start with like a trivial product state with G symmetry. It's a paramagnet. And then we decorate, we put like a SPT phases on some locus, codimension 1 locus of the space, and then gauge the whole, then gauge G symmetry on the whole space. Then, like we obtain the G-gauge theory with the location of the symmetry defects on the like a location of the SPT in the original setup. So this is some SPT defects like which corresponds to some decoration of the SPT like before gauging the symmetry. And the field theory level of it is defined by some like putting a topological term on the codimension 1 some manifold of the spacetime, and this is some electric operator in D dimensions. Okay. So these guys are invertible symmetry, and so like let me elaborate more on what is the action of the SPT defects on the like anyons or some extended topological operators. So in general, this SPT defect has a like action acts on the magnetic defects by like a permutation of the one-form symmetries. So so in order to understand this, like we put some magnetic defects on like somewhere in the space, and then like this SPT defects acts by some enclosing these magnetic defects, and then you can like get this permutation action, like this SPT defect acts by like putting the like codimension 2 SPT defects on the this magnetic defects, and this like attached SPT defect corresponds to the twisted compactification of the original SPT around these magnetic defects. And in particular, if you consider this equation in 2 plus 1D, it means that like a magnetic particle is attached to some electric operator. So this SPT defect induces some permutation of the anyons in general. So here, let me give you some example.
Question.
Yeah, sure. Yeah.
Does it always act trivially on the electric charged operators, like in say?
Yeah, what's your question? Like this slant product is invertible electric operator.
So I'm saying instead of a magnetic defect, if you had an electric defect, let's say in 3D Dirac-Witten theory, what is the action of generally of this SPT defect on it? Is it trivial?
Sorry, what is the setup? This V is a non-invertible, you mean?
No, V is the same. I'm
Okay.
saying, so here you're acting on a magnetic defect labeled by some conjugacy class, right?
Right, sure, yeah.
Instead, if you what is the action on a defect labeled by a representation of the group? The electric charges, yeah.
Right, so, okay. So suppose that we have this like a figure on the torus, like you're seeing the right figure on the torus. So in this case, like if you have like a holonomy G around this X direction, like the gauge field has to be like a commuting pair on the Y direction. So like a Y direction, like holonomy in Y direction has to be like varied in like a centralizer of this G. So this slant product guy is valued in the rep of the centralizer. So like this is in accordance with like a level of the anyons of the like quantum double model or G-gauge theory, where the like anyon is labeled by the conjugacy class and the rep of the centralizer. So this slant product guy now corresponds to some rep of the centralizer. Yeah, like this is a natural like a definition of the slant product for the case of the non-abelian like groups where like a G carries a non-trivial quantum dimensions.
I see. So if G is trivial, this representation, this slant product would also be trivial, right? Because you'll compactify with the trivial flux.
Sure.
And
yeah.
so you'll just have a trivial action on any electric charge line.
That's true. Yeah.
I see. Okay. Thanks.
Yeah, thanks for the question. So let me give you the example. Like this is the simplest. Like Z2 times Z2 case theory in 2 plus 1D. So in this case, so we start with like a pair of the Z2 paramagnet, like a stacking of Z2 paramagnet. And so we have a Z2 times Z2 symmetry, trivial product state with Z2 times Z2 symmetry. And then you put the cluster state. Then you get Z2 times Z2 in the whole system. And then we end up with some location of the symmetry defects of the Z2 times Z2 case theory. And this guy, this defect, green defect, permits the magnetic particles M1 to M1 times E2 and M2 to M2 times E1. Okay. So this is a non-trivial combination of anyons. Right. Sorry. So now let's consider soft action of the 2 plus 1 dimensional finite case theory.
Sorry, can I ask a question?
Sure. Yeah.
Can I go back a couple of slides in this formula for the so you had this cohomology groups like in the previous slide.
Yeah,
In this slide. So even if you take the trivial element of HDBG value in U1, this might give you a non-trivial action, right?
What do you mean the? Oh, let's see. Are you considering in some co-boundary or some?
No, I just have in mind, even in this case of Z2 times Z2. So if I understood correctly, taking the non-trivial element of so the non-trivial SPT means that basically you are constructing the condensation defect with discrete torsion for the gauging of Z2 times Z2, right?
Yeah, right.
But if I'm not wrong, in that case, even if you put trivial discrete torsion, you will still get a non-trivial defect. Should be something like charge conjugation.
That's like a non-invariable defect, right? Like that's like pair with Cheshire string.
Right, because you're okay. I understand, because you're only gauging the electric lines. You're not gauging both.
Yeah, that's like if you don't
understand.
have a discrete torsion, you get the non-trivial stuff, like a non-invariable stuff. Yeah.
So basically, okay, so essentially the trivial elements in that group give you something that it's trivial up to condensation.
Yeah, you could say that. Yeah.
I see.
Yeah.
Thanks.
Right. Any other questions so far? Okay. So let me move to the soft action symmetry. So I talked about some generic invertible symmetry in the finite case theory, but some of the zero form symmetry do not permit anyons. So this was first pointed by Davidov. So let me explain this in detail. So the subgroup, a specific subgroup of the outer automorphisms. Let me write it as out with some like indices soft SF. So this guy is what Davidov calls the double class preserving outer automorphisms. So if you like choose some like specific finite gauge theory, specific finite gauge group, sometimes we can find weird outer automorphisms where it is a non-trivial outer automorphisms. But if you take any commuting pair of the G and H, like any commuting pair of the group elements, this acts trivially on these commuting pairs. So it means that like recalls that the Hilbert space on the torus is labeled by the commuting pair of the group elements. So this like a subgroup of the outer automorphisms acts trivially on the torus. So it doesn't permit anyons. So like this is a example of the soft autoequivalences he talked about. And also the subgroup of the SPT defects also have this kind of action, trivial action can have a trivial action on the torus. So this subgroup H2 soft, it just means that the SPT faces with a trivial partition function on the torus. So it means that like a permutation action of the magnetic defects is trivial because the strand product is trivial. So there's no permutation of the anyons induced by this SPT. So these are kind of a faithful symmetry that acts on the Hilbert space faithfully. But if you focus on the just torus Hilbert space, it's just by a trivial action, so it doesn't permit anyons. So this class of the symmetry is called the soft-plated autoequivalences by Davidov. And here in this talk, I want to clarify how this soft symmetry acts on anyons, mainly shown by examples. Okay. Right. So in order to kind of clarify how the symmetry can act on anyons, let me very briefly review the some data of the braided autoequivalences, which is kind of a skeletonized way. This is based on the Station Q people's paper on the symmetry fractionation, which is kind of very famous. So first of all, invertible symmetry can act on anyons by a permutation of the labels. So this is a left top formula. There's this psi is action on the symmetry, and A is the label of the anyons. So this can act by permutation of the anyons, which is trivial for the soft symmetries. But even if these guys are trivial, this permutation action is trivial, this can act on the fusion spaces. This symmetry can act on the fusion vertices of the anyons. So this V on the right top is a vector space, a Hilbert space carried by the fusion vertices. And the symmetry can act by some unitary matrices U on these fusion spaces. Okay, and then the braided autoequivalences requires the basic data of the modular tensor category 2 plus 1D TKFT to be preserved under the symmetry. So it means that this R symbol, F symbol, half braiding or associators possibly permuted by any gets anyons permuted with some non-trivial action on the fusion vertices, and it can be transformed in the this kind of way. But after these symmetry actions, F and R should be invariant under the symmetry action. And also, on top of this, there's data of the symmetry fractionalization, which is that if you consider the junction of the zero-form symmetry defects, these anyons can be acted by these junctions by some non-trivial fractional charges or some phases. Okay, so this is some setup for the zero-form symmetry of the 2 plus 1 dimensional TKFT. So let me mention, so what's the non-trivial effect of the soft symmetry on anyons? So it cannot permit anyons, but still it has a non-trivial action on the junctions of the anyons. So this is always non-trivial. Some of the U symbol has to be trivial. Because this controls the non-trivial symmetry action on the higher genus surface, as I explain later. But meanwhile, the fractional charges of the symmetry, which is basically how the junction of the zero-form symmetry defect acts on the anyons. So these fractional charges can be completely trivial, which is actually the case for the SPT defect in general. So in other words, in some cases, soft symmetry can be purely acting on the a fusion vertices, no other non-trivial effects. So this in other words, soft symmetry can be a so-called vertex scale transformations. So vertex scale transformations is action this is just the action of the unitary matrices on the fusion vertices. So usually this is regarded as some redundancy for the expression of the modular tensor categories, because it is gamma, arbitrary choices of gamma can transform F and R symbols, and it gives you the distinct data, distinct modular F and R symbol for the same TKFT. But in some cases, this gamma can preserve the F and R symbol completely, and then still this gamma cannot be trivialized by its natural isomorphisms. And in this case, this gamma vertex gauge transformation gamma can generate a non-trivial global symmetry. So this is a kind of extremely subtle case, extremely subtle action of the global symmetry, which I think is sort of interesting. So any other questions so far? I'm going to explain some examples.
Yeah, if I may. So, are you anticipating that there is an operator that acts on all of space, like a zero-form symmetry that implements this transformation?
Yeah, there's I can write down the explicit final
And in
steps.
what sense? And in what sense is the state before and after? Are the state before and after different?
Well, so basically, this symmetry just acts on the state by a phase. So like symmetry action becomes some.
No, I understand that. Maybe I'll rephrase the question.
Yeah.
Is there anything in the theory that carries charge under that symmetry?
Yeah, I can write down the specific anion diagrams, and the symmetry acts on it, and it gives you some invariant. And so
No, I have a state at some time 0.
Right.
And then imagine I have an operator that acts on it.
Right.
And act with the symmetry operator before and after. Am I going to get a different? Is there an operator for which I'll get a different answer? In other words, there's an operator that implements this transformation. Is there any observable in the theory that does not commute with it?
Oh, that's yeah. Let's see. Yeah, I think so. Yeah, I guess we can imagine the so I guess we need to create some like a state in the presence of anions, like that corresponds to the specific fusion vertices, like a fusion diagram of the anions, and then like this symmetry operator acts on the this like a state in the presence of anions, and the like depending on the like a fusion diagrams that corresponds to the state, it gives you the some non-trivial, it acts by some non-trivial U symbol. Like a U symbol has to be non-trivial for these kind of soft actions. So this can act non-trivial on the state in the presence of the anions in general.
So can this be interpreted as a local operator stuck at the point where the anions split?
Let's see. Yeah, well, I have a microscopic lattice model, which is a quantum double model, and I can write down a finite depth circuit, which implement it. And in this sense, this is this can be expressed in terms of some a local symmetry action. Yeah.
Thank you.
Yeah, I can show you how this acts non-trivial on the junction of the anions later at the microscopic levels. Yeah.
Thank you.
Yes, makes sense.
May I ask a question? Sorry. I want to make sure that I understand the claim. So you say that you have some vertex transformations that are pure gauge, and you still want to call those a symmetry. Is that correct?
That's right. Yeah, that's right.
And can you do, for example, compute like a twisted partition function, like a partition function in presence of a background for this symmetry? Can you twist the theory by the symmetry?
Sorry, could you say again?
Can you compute like a twisted partition function for this symmetry? Is that symmetry for which you can turn on a background?
So you want to gauge the symmetry or just the background?
No, just the background.
Well, in some cases, yes. In later
even when it's pure gauge, you still can turn on trivial background, and you get a different.
Yeah, that's true. I can do that. Well, I can show the example where the so in some cases the symmetry can be generated by some SPT. And so in this case, there is even Lagrangian description for in terms of the for this soft symmetry in terms of the gauge fields, and I can turn on the background gauge field for this symmetry. This is basically just like a digraph with them, it looks like some twist on the gauge theory. Yeah, I can do that.
Thanks.
Yeah, depending on example.
Sorry, I'm confused with the question. Why are you claiming that it's pure gauge? I thought it is just a zero form symmetry.
Yeah, it's a kind of weird notation. Like some people call this gamma matrix that acts on the diffusion vortices by the vertex gauge transformations, right? Because basically this terminology comes from the fact that this gamma acts by some gives you some redundancy for expression of the theory, in terms of the F and R symbol. This gamma acts by some basis change, and generally transforms the F and R symbols. But my claim is that some specific gamma matrix should be regarded as a action of the symmetry when this gamma preserves F and R symbol, and then in some cases gamma turns out to be not trivialized by these natural isomorphisms and acts non-trivial on the theory. And in this case, this gamma is identified as a global symmetry action. Yeah, I just mean that.
So is it or is it not generated by a? You're saying it cannot be generated by the thing on the right, or
could you say again? Sorry.
Are you saying it cannot be generated by this thing on the right?
Yeah, it cannot be generated. Wow, this natural isomorphism acts on a Hilbert space completely trivially. So this is a trivial action. In some cases, the gamma matrix cannot be trivialized by the natural isomorphisms. Yeah.
Okay.
Yeah, this is a case.
Clear on your response to his question. It's basically, I can't read the sentence. Do you mean that it acts like this where gamma does or does not have the form at the end of the sentence? I guess this is Nat's question.
Yeah, right. So this natural isomorphism is basically equivalence class, or the equivalent action of the gamma matrix on the Hilbert space. So a faithful symmetry action is not expressed in terms of the natural isomorphisms. It cannot be trivialized by, we can think of the multiplying the gamma matrices by some arbitrary natural isomorphism with arbitrary choices of small gamma. I cannot trivialize some a given gamma by any choices of the natural isomorphisms. And then I identify this gamma by some a faithful symmetry action. That's what I mean.
You mean that it cannot be, it is not equivalent to what you wrote?
Well, sorry, I guess my writing and the
question is about English, I guess.
Yeah, I think that's a problem of the my last sentence. Okay, let's see. So yeah, this last sentence means that a pair of the gammas has an equivalent same action on the Hilbert space if this is related by the natural isomorphism. Yeah, sorry, this last sentence is not good. But the non-trivial action on the symmetry, if the gamma gives you a non-trivial action on the symmetry, it cannot be realized by natural isomorphisms.
So it's inequivalent under the natural isomorphism.
That's true. That's true. Yeah.
Okay, thank you.
True. Yeah. Yeah, sorry for the confusion.
And does it make sense to turn on a background field for the soft symmetry only if gamma cannot be trivialized by natural isomorphisms?
Well, we could turn on the background gauge fields of the completely trivial symmetry in principle, but yeah, that's possible, right? We can turn some identity operators, some symmetry, and turn on the background gauge field, which is just a trivial operations, but it makes more sense that when gamma is non-trivial, I can insert the symmetry defects. Yeah, it makes more sense. Yeah.
Sorry, a very quick last question. Can there be non-trivial examples with a billion topological orders?
I don't think so. My example is highly non-trivial. This is because well, I haven't checked, but at least for the SPD defects, any SPD defects act on the torus. There's no weird guy which cannot be detected on torus, but detected on a higher genus surface. So
yeah,
a very topological order doesn't have this kind of genus 2 detection operators, at least for SPTs. Yeah, I guess that's also true for this auto-automorphism stuff, but yeah, I guess so. So like the examples which is discussed in literature is like always highly non-abelian.
But I guess the point is that for a abelian topological order, the junction spaces are always one-dimensional, right?
That's true. Yeah. Well, like actually in the example, I haven't like this U symbol just acts by phases. I haven't checked like a fusion multiplicity is 0 or 1, but yeah, there's not much difference. Like yeah, no need to just actually talk about fusion multiplicity.
I see. Thanks.
Right. Any other question? Okay. Let me go ahead with some examples of these kind of soft symmetries. So let's consider this finite group of the order 128. This is a non-abelian group. So it looks a bit complicated, but this is basically just a central extension of the Z2 group by a Z2, like a Z2 to 4 by Z2 to 3. So it's not as stable as what the order looks like. So we have 4 elements that generates Z2 to 4. Like this is a P, Q, R1, R2. And the equations written in here characterizes a central extension of this finite group. And so this central extension is okay. And then this order 128 group has a 1 plus 1 DSPT phase, which looks pretty much like a cluster state of the Z2 times Z2 symmetry. So this topological term for the topological response for the SPT just looks like a cup product of the one-form gauge fields, NP and NQ. This NP and NQ is basically a Z2 gauge fields, like a one cocycle for the P and Q. So formally, it is a one cocycle counting the model 2 number of the P and Q appearing in the expression of the group elements in terms of the generators. So this is basically like a P and Q Z2 gauge fields. So action just looks like a cluster set. But here, this central extension is carefully arranged so that we cannot turn on the P and Z to P and Z to Q gauge field at the same time on a torus. But we are allowed to turn on this kind of gauge field on the genus 2 surface. And it is a funny fact that even before the Davidov's work, like Polman and Turner already discussing this weird SPT phases on his appendices, their appendices on the string of the parameter. It's kind of a 1 plus 1 SPT paper in 2012. Okay, so this is an example of the SPT phase in 1 plus 1D with high genus detections. So there's no torus with gauge field which can have a non-trivial value of this SPT. But if you take the genus 2 surface with a background gauge fields of the G, you can consider you can detect this SPT, and this turns out to define the soft symmetry from the SPT defects. Okay. Right. So basically, so let me more carefully look at how these SPT defects act on the junction of the magnetic defects. So these SPT defects basically just acts on the junction of the anyons, like in particular magnetic defects, just magnetic defects by a phase factor, some bolts, it can be understood from the if you have a junction of the gauge fields, the SPT phases has some 1 plus 1 SPT phase has some a Boltzmann weight factor, which gives you the phase, when we see the junction of the background gauge fields. So basically this SPT phase acts on the junction of the magnetic defects by this kind of phase factor. But in order to make exact precise correspondence between this cocycle and the braided auto equivalences, it is actually a very non-trivial job to directly relate this omega and this graded autoequivalences data. I spend some time to figure this out. So for instance, a generic cocycle for SPT, if you take this cluster set action, unfortunately this a choice of the cocycle for the SPT doesn't leave the R symbol invariant. So to see this, let's consider a half grading between this P and Q magnetic defects. And then this SPD defect basically measures intersection number between P and Q magnetic defects when projected onto 2 dimensions. So this half grading picture has some intersection at the this center of the half grading, and in these particular choices of the cocycle gives you some minus sign. And this is kind of technical point, but so the lesson here is that in general, we can't use naively use a generic cocycle as data of the graded autoequivalences. But here, one can find the explicit a deliberate choice of the cocycle, which is symmetric under the group elements, omega GH equals to omega HG. And in this case, we can explicitly find a cocycle representative which leaves the R and F symbol completely invariant. And then I can use this data as some data of the graded autoequivalences. Okay, so this is a kind of technical point to find the correspondence between the SPT and the graded autoequivalences of the soft symmetry. And then after finding this, I can figure out this action of the U symbol, which is some explicit choice of the cocycle for this 1 plus 1 SPT, soft 1 plus 1 SPT. And so this U symbol is non-trivial. So the data is completely trivial. The symmetry fractional data and the permutation action is completely trivial. So this U is the only non-trivial data for characterizing this symmetry. So in this sense, this is purely vertex gauge transformations. And then, so this action on the junction is important, which characterizes the faithfulness of the symmetry action. For instance, this characterizes action on the genus G Hilbert space. So generally, the genus G Hilbert space is labeled by these specific anion diagrams. So in the case of the genus 1, it just corresponds to the cross diagram of the single anions. And then if you have a genus 2, for example, it involves some anion diagram connecting the 2 cycles. So now it involves a higher genus diagram involves some junction of the anions, and that's why this U symbol becomes important to characterize higher genus actions. And then I can compute the action on the genus 2 surface with some specific choice of the state becomes a minus sign. So in this sense, a specific choice of the state is acted by some non-trivial sign under the symmetry action, and this minus sign is invariant under non-natural isomorphisms. So it means that this is an example of the non-trivial vertex gauge transformations where this U symbol cannot be trivialized by a natural isomorphism, and it gives you the phase fraction of the global symmetry. Okay. Any question about this example? Right. So
actually, can you write chi in the previous slide?
I can write down chi. Well, this is a.
What does it look like?
This is actually very complicated. I have an appendix in the paper.
Okay.
I take a look at that. This is a very complicated. I spent some time to figure it out. Yeah.
Okay.
Yeah.
And this omega SF, you say that it defines the U symbols, so they are diagonal, right? These U symbols.
Yeah, this is diagonal. This has a diagonal action on the Hilbert space.
So is it possible to kind of view these soft symmetries as some kind of representation of something, like these U symbols as maybe there's a module category structure?
Well, it's so well. Can you hear what kind of the presentation do you want?
Like the simplest case, a group perhaps, like a abelian group in degree 1, only acts on the morphisms, but it's probably not the case here.
Well, I don't have a good answer to your question, but
okay,
yeah,
that's fine. Thanks.
Yeah. Any other question? Okay, so let me give you some several remarks about this soft symmetry. So first of all, I talked about this soft symmetry with the genus 2 directions, but there is a even more softer symmetry, which cannot be detected within the genus smaller than G, but it can be detected on genus G. But this corresponds to the this corresponds to the fact that I can explicitly construct some family of the 1+1 DSPT phases with some higher genus property, which is again given by the central extension of the Z2s. And this guy has this higher genus detection properties. And it means that I can use this SPT effect to construct some global symmetry, which acts trivially on some fixed genus, but within some fixed genus, but it acts non-trivially on the genus G. I can consider this kind of the weird example. And related to the Diego's previous questions, I can explicitly write down some background gauge field coupled with this kind of SPT symmetry. This is kind of not hard. So if you have a SPT action omega for the SPT phase, I can just turn on the background gauge field by coupling the background gauge field A cap omega, and this is just generated by the symmetry given by SPT. And in particular, this kind of the soft symmetry can be gauged. And then this soft symmetry also it looks completely trivially on a torus, for example. But after gauging this soft symmetry, you get a distinct theory from trivial distinct theory from the untwisted case theory, which is solved by just a stacking of the Z2 times G gauge theory. And this A cap omega gives you the non-trivial digraph fit and twist after gauging the soft symmetry. In particular, this Z2 magnetic defect carries some projective representation for the G symmetry and becomes non-invertible.
Sorry, can you give me some intuition why this can you give me some intuition why this higher genus detection is possible? Because I thought that if you fix the action on all the junction spaces, the soft symmetry is fixed, isn't it?
No. So this is some a generalization of a Paul Montana's group. So I can write down some genus G gauge fields, where the first cycle has a P1, Q1 as a background gauge fields, and then second cycle has a P2, Q2, and the third cycle has a P3, Q3, and it is closed with PG and QG.
Okay, but apart from the details of the group, I wanted to understand from the point of view of the action on the anyons. So before you were explaining that this soft symmetry arises because the symmetry basically doesn't permute the anyon but acts non-trivially in the junction spaces.
That's true. That is also true for this higher genus surface, I guess. Yeah.
Well, but every higher genus surface, I can decompose it in pair of pants, and then the action will be reduced to the action on the junction spaces. So, how is it possible that? So, because are you saying that up to a certain genus, even though the action on the junction space is non-trivial, it could be that the full action is trivial and you can detect it only after a certain genus?
It should be. I'm explicit action on the junction for these higher genus functions, but it should be, yeah.
So still the junction the action on the junction spaces is non-trivial.
Yeah.
But it happens that say up to genus 10, I don't know.
That's true.
All these spaces cancel and you have a trivial action, but you complete at genus 11 and you get a non-trivial action.
That's true. Yeah.
Okay,
Yeah.
interesting.
Yeah.
I have a related question. Imagine I didn't know you have that symmetry. So I'm looking at the modular tensor category and I didn't notice that there's another symmetry.
Mm-hmm.
Did I see that some correlation functions vanish in a surprising way? So that is something that would violate the selection rule that is the underlying reason for this. So the asymmetry will lead to some selection rules and therefore some amplitudes would vanish. I wonder whether I would notice it even if I don't have the even if I don't notice that the symmetry is there. I'm sorry, I kind of got the question.
Well, this property of the soft symmetry, we can't do anything on the if you just act on the Hilbert space, you cannot do anything on the torus or some specific genus. Only when you look at the genus G surface or some specific.
So I'm looking at some genus G and maybe I have some anyons and they braid or something. So I get a partition function.
Yeah.
And imagine it violates the selection rule that is implied by your symmetry. So I guess you would say that it vanished. The amplitude has to vanish.
Mm-hmm. Yeah.
So is there any other way of understanding why this amplitude vanishes without your symmetry? It would be very surprising that so many amplitudes vanish.
Well, not that I know, not on the top of my head. And this is a very extremely subtle action of symmetry. And generally the lesson is that we need to, in order to find this symmetry action, we need to go into the very higher genus. I don't have a good answer to your question. Yeah.
Thank you.
Yeah. Any other question? Okay, so let me give you the second comment. So some of zero-form symmetry of the 2+1 dimensional topological faces has a so-called H3 obstruction. Now this is basically the a two-group structure involving the zero-form and the one-form symmetry of the TKFT. So for instance, if you have in general, if you have three junction with the three zero-form symmetry operators, I can talk about some point junction of the zero-form symmetries, and in principle, this point junction can emit some one-form symmetry generators, and this is a signature of the two-group structure between the zero-form and the one-form symmetry. And in the case of the 2+1 TKFT, this two-group structure is characterized by this O3 class, which is some certain group cohomology, valued in the group of the abelian one-form symmetries, invertible one-form symmetries. And this is called the Postnikov class, kind of the generalization of the extension class for the groups. And it is known that when the invertible symmetry acts on the junction on the anyons completely trivial way, say U equals to 1, then the H3 obstruction, this two-group structure becomes trivial. The trick is that if U equals to 1, then there's some certain consistency condition between this U and the symmetry fractionation data, eta. And then it means that the eta has to be, symmetry fractionation has to be some valued in some specific homology class H2. And then this first equation written in the slide basically means that this O3 is given by some derivative or co-boundary of this eta. And then since eta is closed, this O3 has to be also vanishing because the O3 equals to d of eta basically. So regarding this, it is often said that like S3 obstruction becomes trivial for the non-permuting symmetry based on the belief that like this U would become 1 for the like non-permuting symmetries. But this is actually the case for the SPT soft symmetry, because in the case of the SPT, like this fractionation class eta is trivial, so O3 turns out to be also trivial. But it is not still open question, like whether the non-permuting symmetry leads to the like a trivial H3 obstruction two-group structure. Especially, I'm not sure whether the two-group structure is trivial for the like a soft version of the auto-automorphism of the G-gauge theory. This is an interesting open question, I think.
Sorry, what's an example of the soft outer symmetry? Like if it permutes conjugacy classes, shouldn't it permute anyons?
I quite forget the specific example, but the mathematician already discusses this. Like there's some like a bunch of paper David of sites, and the like this Newman and Zickman like this kind of like 2 or 3 mathematicians paper has examples of the non-trivial double class preserving groups. So yeah, I recommend you to take a look at the paper. Yeah. Yeah.
So is it the claim that it preserve all the conjugacy classes? Maybe?
Let's see. Yeah, well, it should, because the like it doesn't permit anyons, because the like any commuting pair is left invariant under the, yeah.
Okay.
Yeah. Right. Yeah, thanks for the question. Okay, so let me go to the like how long minutes I have.
I mean, there were a lot of questions, so maybe you can take another 5 to 10 minutes or so.
Okay, sure. Yeah. So let me briefly discuss the like microscopic lattice models. So the whole message I have is like this order 128 like a soft symmetry action can be realized in the quantum double model that describes the finite case theory. So since it has like a order 2 to the power 7, like I have like a 7 qubits per edge. And then like I can write down some Topological type lattice models, which describes this finite gauge theory of the where the soft symmetry is present. And then I can also write down the like this C2 soft symmetry generated by the finite depth circuit. So like given that the like a symmetry is generated by the this cluster state type action involving 2 of the C2 symmetries, I can explicitly write down some finite depth circuit on the quantum double model, which generates the Z2 symmetry. And this corresponds to the specific SPT defect, which I discussed earlier. And meanwhile, the generic anyons can be represented by a so-called ribbon operator. This is basically some combination between some gauge transformations that correspond to magnetic defects and some delta function that corresponds to something electric, such as electric charges. Okay, and then sorry for rushing, but I can basically show that this cluster state operator, this telephone symmetry operator, acts on the this ribbon operator in a completely trivial way. Because this R a telephone symmetry operator is basically the a product of the control Z, and this ribbon operator for the magnetic flux is basically the product of X power X. So basically this R acts by some attaching the power Z to the ribbon operators. But recall that this ribbon operator has some specific delta function, which trivializes some holonomy along the ribbon, cross ribbon. Then this delta function basically trivializes this product of power Z. And then after all, this Z2 symmetry doesn't permit anyons. But it turns out that if I consider the junction of the ribbon operators, this Z2 symmetry acts by a non-trivial phase, which is associated with the junctions of the ribbon operators. So this is inconsistent with junction of the action action on the junctions I have discussed earlier, use simple operated autoequivalences. So there's a microscopic description which in accordance with the TKFT descriptions. So okay, let me give you the brief. Let me give you a remark about the classification of the gapped boundaries and some implication to the 1+1D gapped phase with the non-invertible symmetries. So this kind of soft symmetry I have discussed earlier leads to the distinct gapped boundary of topological order with the identical condensed particles. So this can be seen by us by follows. So if you consider the G-gauge theory in 2+1D, the gapped boundary is labeled by the pair. So one of them is a spontaneous breaking of the gauge group at the boundary, and the second term is some boundary topological term, which is labeled by the second cohomology alpha. This is valid for the untwisted gauge theory. Then let's consider the 2+1D gauge theory of the finite group where the soft symmetry present. Soft symmetry generated by the SPT defects. Then there is a pair of the gapped boundaries. So one of them is just a vanilla Neumann boundary condition, which doesn't break the symmetry gauge group on the boundary. This just condenses the magnetic particles. And the other gapped boundary is a twisted version of the Neumann boundary condition, which attaches this soft SPT. So since this omega SF doesn't permit anyons, both of them condenses the magnetic particles. So it has the same Lagrangian algebra object, formally speaking. So it is both of them given by a sum over the magnetic defects. But still the Lagrangian algebra itself is different because the structure of the Lagrangian algebra becomes distinct because there are more subtle data of the Lagrangian algebra, which has to do with a multiplication morphism, L and L fuses into L. And since this symmetry acts on the junction of the anyons, this guy is modified by the soft symmetry actions.
The question?
Right. So, sorry. Yeah. So
if you have two different soft symmetries, one which can be detectable at genus G and the other that can be detected at G prime, how do the structure of those corresponding Lagrangian algebras differ? What data distinguishes those two?
There's some way to characterize Lagrangian algebra in terms of some modularity, right? For instance, you can put a Lagrangian algebra, a gapped boundary on a torus and study some mapping graph group invariance of the Lagrangian algebra, and then give still some a bunch of the conditions, inputs on the coefficients of the Lagrangian algebra, and then we can do the same game for the higher genus. And it gives you some a specific modularity condition on the Lagrangian algebra, and this can eventually detect a distinct two Lagrangian algebra. But given that there's a softer symmetry, this kind of the modularity condition within some specific genus can never be sufficient condition for the characterization of the Lagrangian algebra.
Shouldn't it just be the algebra structure is different? So the anyons that condense are the same, but the actual structure as an algebra in the, in the 3D the TQFT, that's different, right?
Yeah,
and that's all consistent with what you're saying about that there's an action on there's a difference on the junctions. And so you see that in the algebras.
Yeah, that's true. Yeah, I agree. Right. So, okay, finally, let me discuss the implication to some 1+1D gapped phases. So we have learned that there are two distinct gapped boundaries of the same G-gauge theory where the condensed particle is completely the same. So this can be used to say something exotic about the a classification of the 1+1D gapped phases with a non-invertible symmetry. So here, let me summon the symmetry TKFT, which is now a very hot topic about regarding the classification of the phases with non-invertible symmetries. So here, the gapped boundary can be used to describe the gapped phases in 1+1D, using this sandwich picture. We have like a 2+1, like a slab of the 2+1D gauge theory, the paired, like sandwiched by a pair of the gap boundaries. So let me think of the like two kinds of sandwiches I can think of. So so the first phases has a sandwich like where the both of the side is given by the like just a pure Neumann boundary condition, and the other sandwich is G-gauge theory where the like one of them has an untwisted Neumann boundary condition, the other has the twisted version of the Neumann boundary condition. Okay, so then it has a completely the same like a topological like a symmetry operator because the symmetry boundary condition is both of them are given by like a Neumann boundary condition. It's both of them has a Lefty symmetry, and also it has a same pair with the order parameters. It's like this is a topological operator stretching between the intervals. Gives you some local operator after shrinking the interval. So same set of the order parameters, same set of the symmetries. So both of them gives you the distinct like same symmetry breaking pattern of the Lefty symmetry. In both cases, the Lefty symmetry is free broken, but still these two guys are distinct phases. Like if you want to go one from the to the other, like it has to experience a phase transition. So these guys are regarded as a dual of the like SPT transition between the SPT transition with like this soft G symmetry. If you gauge the like a transition SPT transition, you get this like distinct Lefty SSB phases. And in many cases, like this kind of non-random transition, something like this kind of the SPT transition, like a non-random transition, it can be understood as some like SSB after SSB or non-invertible symmetry after like taking the dual discussion by gauging. Like this is sometimes called a generalized random paradigm, but it serves as some exceptional case where even you gauge the symmetry, like you cannot distinguish them by a symmetry breaking pattern. And for instance, these two phases are like distinguished by the genus 2 partition function or the SSB phases. Okay, so the last part of the talk is a 3+1 dimensional gauge theory, but I guess this is kind of a topic I can skip over. So the message here is that we have like a 3+1 dimensional Q8 gauge theory, like which has a similar properties to the like soft symmetry in the sense that if you consider the specific SPT defects for the zero form symmetry of the 3+1 dimensional Q8 gauge theory, this has a completely trivial strand product, and it doesn't give rise to the like non-trivial higher categorical symmetries or higher group symmetries, but still some of the SPT defects has like extremely subtle symmetry action where the higher group is trivial, but still it acts on the junction of the magnetic defects. So this is an analog of the soft symmetry, which is also observed in 3+1D. Okay, so this is my summary of talk. That's what I want to say today. Thanks for the attention. Yeah.
Great, thanks very much for this nice talk. Are there more questions? Maybe I can start off with a question. So you were making this point that if you have gap boundary conditions that correspond to these different choices of this omega soft or something, yes, and
Right.
then there's a distinction in the gap phase. Now you can just classify all the Lagrangian algebras given the sim TFT for some group like symmetry, for example.
Right.
And so and that set contains all of these things that differ by these omegas. And is it clear to you that all such instances will be related to this sort of soft symmetry? Is this sort of the same thing? Because mathematically you can just sort of classify when you can have distinct algebra structures on a given set of anyons.
That's right. That's right. Yeah, it's not apparent to me actually. Like, well, like if there's
I don't think so
if
either.
this kind of the Lagrangian algebra with same Lagrangian algebra object is related to by soft symmetry or not. Like this is not apparent to me. I don't think it's.
So it's like an instance of this, but it's not that any of these instances come from this. Okay, thanks.
Yeah, so Davidov was actually like
he has the classification.
But Davidov, like all the Davidov's example, like he had is associated with this soft symmetry action, but in general, it's not apparent. Like especially when this is theory, like especially when the bulk is not like case theory, like generic TQFT.
Some generic fusion category double.
Yes.
Okay, Rajan, you have a question?
Yeah. So if we have a non-trivial action on the fusion space, but suppose the action is trivial on a genus G surface for any genus, then is that action necessarily a natural isomorphism?
Oh, yeah, that's a good question. So you're talking about the symmetry action which is completely trivial on any surface.
Yeah, on any genus. Yeah.
Well, I guess it should be natural isomorphism because the symmetry action is not faithful. But well, I'm not sure. I can't say the like a rigorous statement, but it should be natural isomorphism in the sense that it is not a faithful symmetry action.
I see.
Yeah.
Because I was thinking that if you act on the fusion space with a matrix or a phase, which cannot be written in terms of these small gammas, can such an action always be detected at some genus? Because that seems like there are too many soft symmetries, right? If you can act with anything that cannot be written as these gammas.
Sorry, could you say again? Like, what kind of the gamma are you talking about? Are you talking about gamma?
Yeah, so suppose I have a capital gamma, which is non-trivial action. Suppose it cannot be written as a natural isomorphism. Can it be detected at some genus? Which is like the context of this question. Yeah.
Yeah, like first of all, like we cannot like take like a very generic, like most generic gamma as a symmetry action because see this gamma still has to like preserve this like F1R symbols. And there's a statement of rigidity saying that like if this gamma preserves the F symbol, like there's only a discrete classification of these vertex case transformations up to natural isomorphisms.
I see.
Yeah, so this is a result of the Okunyan rigidity. And so so in this sense, like this gamma has like a only finite classification, generates only finite symmetry group. So right, so yeah, you can't think of the two generic gamma, but I believe that if this gamma has like a trivial action on all of the genus, then it's just like a trivial symmetry action, so it should be natural isomorphisms.
Okay, thank you.
Yeah.
I have a related question.
Sorry, Arkia put his hand up. Let me. If it's related to exactly this, go ahead. Maybe it's unrelated.
Yeah, it's related to the. Yeah. So let me fix the rank of the TKFT. I guess there should be a bound on the genus such that if the action is trivial up to genus G, then it's always trivial. Because I couldn't. I hardly imagine that if you have a low rank TKFT, you can have an action that is trivial, say up to genus 1000, but it starts to be non-trivial genus 1001.
Yeah, that's intuitively makes sense because like if you have how to say this in like so I guess like your statement responds to the like saying that like if you have some fixed like if you have a very large number of the genus, I guess maybe like it's kind of a combinatorial program, like we have to enumerate like of what kind of the like anion diagrams is allowed in this like a genus G diagram. But like I guess like if you go like to the very high genus actions at some point like this anion diagram is cut off. Like you need to have some like a trivial leg in here, and then like it should reduce to some action of the like lower genus actions. So in that sense, maybe, yeah, I guess you're right. I guess
it might be practically useful to derive such a bound of the genus in terms of the rank, so you don't need to check arbitrary high genus to understand whether
for fixed rank maybe it's
not.
For that, for fixed rank variance maybe useful, like develop this kind of bound. That's agree. Yeah, sounds good.
Yeah.
Yep. Yeah, thanks for the nice talk. I was wondering, you showed this picture with the ribbon operators, and you showed how the soft symmetry acts on the junctions. Is there a way to like construct some correlation function, like Nati was saying earlier, where you take these ribbon operators, you form some closed diagram, which you can act on your Hilbert space, let's say even on a sphere, like genus 0, right? And then you act with the symmetry on that. Is there a way to like detect the symmetry action from like some like operator product in time?
Yeah, I think so. Yeah, like so what I can find microscopically is that like if you have this junction of the ribbon operators, like this like CZ operator R can like act on this like a junction by phases. So like even for the sphere diagrams, like if I have like this kind of the genus 2 like diagrams, like some the genus 2 diagram embedded in a sphere, I guess we should be able to find a non-trivial action on the sphere with specific insertion gradients. Yes.
And I see, which you can do with the ribbon operator, I guess.
Yeah, right. So we need to insert some like specific anion diagrams and the compute the symmetry action, like sweep the symmetry action over this anion diagram.
Right. I see. Okay.
Could both the phases cancel, like if you're on a sphere?
Oh, let's see. Yeah, I'm not sure. Well, might be right. If you
So like, do you have to go to a torus then? Is that the minimal one?
So yeah,
like the phase you compute is sort of like the cocycle like evaluated on that surface.
Yes,
right?
that's true. Yeah, like that's a good point. Like if you just consider closed anion diagrams, like if you sweep the defect all over the space and just compute the action on the anions, like then this just becomes like a product of the omegas on the sphere, then it should be trivial. Yeah, that's true. Yeah. So I guess we need to consider some open anion diagrams, for example, or just go to genus 2.
Yeah, so open anion diagrams like in the SymTFT where you have endpoints. When you have these different algebra structures, you detect it in the OPE of these operators.
Right.
So that's sort of maybe the simplest way you would detect that kind of structure, soft symmetry structure.
I think a related question is, can you make the defect like can you open up the defect, like the zero form closed defect? Can you make domain walls of that? If you could do that, then you can do it on a sphere.
I guess that's easy. We can just one way to do this is that like when we construct a quantum double model, we just put this cluster state type SPT before gauging the symmetry, and then it gives you some defects. So microscopically, it's not that hard. Well, the other way of doing this is that we truncate this symmetry operator on some like half space or something, and then conjugate quantum double model by this. I guess that's doable. So it's not that hard to like explicitly insert this symmetry defect. It's pretty much the same as what is done for the cluster state, I guess. Right bottom figure has this procedure.
Yeah. Thank you.
Yes, that's a question.
Okay, so maybe we thank the speaker again, and I will just stop the recording, and we can